So examples. Well, the leading order term is that one. Goes like L, and if you actually calculate it, you learn that it goes like a half mv squared plus gn m1 m2 over r, just from calculating the diagrams. Of course, this was figured out by not using effective field theory methods, but by other methods, by Newton a long time ago. I guess you could say that he knew about the mass of the graviton, in other words, that it's 1 over r, but he didn't know the spin, so he couldn't go any further than this. So the next term in this expansion wasn't really calculated until much later, in 1938, by Einstein, who did know the spin, and his friends Infeld and Hoffman. So from the point of view of effective field theory, what Einstein and his buddies did can be summarized in the following diagrams. So this is the place where the 3 graviton vertex first enters, and it looks something like that. And then you, of course, also have to worry about velocity corrections of the vertices. So Newton exchange, but with a term that's velocity to the first like that. Velocity squared couplings of the vertices. Velocity to 0. Retardation effects, the fact that the exchange is not quite instantaneous. So the time derivative term in the propagator for the potential is a perturbation, so there's diagrams like that. And I guess finally there's another diagram like that, which is a Siebel, and it looks something like that. And then the Feynman rules are completely specified, and it's just termed a crank, and it's not hard to program Mathematica to calculate these things, and you can just do it. Let me just write down the answer they got for the hell of it. So this is the leading relativistic correction to 2-body motion in GR. Actually, yeah, I'm only going to write it for 2 particles. So there's a kinetic term correction, just from expanding out the relativistic kinetic energy. And then there's terms that are corrections to the Newtonian potential. So they go 1 over r, but then they go like powers of velocity upstairs. Where n is just r over the magnitude of r. And finally, there's a non-velocity potential. It goes like 1 over r squared. This is coming from this diagram and from that diagram. In particular, the coefficient here, well, actually this whole Lagrangian, but in particular, well, it's the place where the fact that gravity is nonlinear first shows up. And it's actually, this term in the Lagrangian is what's responsible for solar system test of gravity, like the perihelion shift of Mercury. It comes from this correction to the Lagrangian. So the fact that the 3 graviton term is the way it is has been tested experimentally. By the way, all these coefficients depend on what gauge you're in for the propagator, but of course, at the end of the day, physical quantities do not. So that's second order, and everything has been done up to actually velocity to the 6 and even higher in some terms. But now the rules are clear. So for example, at the next order perturbation theory, at velocity to the 4th, you might encounter diagrams like this, where the 4 graviton vertex comes in, and I don't know, all sorts of stuff, something like that, etc. It took a while longer to compute these things. Traditional gravity methods computed them starting in 1981 all the way to 2002. That's when it was finally settled. People using effective field theory methods, Gilmore and Ross completed that in 2008 using effective field theory. The effective field theory calculation actually just boils down to a bunch of standard loop integrals, one-loop integrals, despite the fact that these things look like two-loop things, in three spatial dimensions. So basically what they showed is that every term in this expansion can be related to a standard Feynman integral in 3 dimensions, which is of this form. 1 over k squared to some power, 1 over k plus some external momentum, q squared to another power. So really, really easy Feynman integrals. To get into this form, there were some, it's a long song and dance about using different tensor reductions and integration by parts techniques. But my point is that they're all standard loop integral methods that one can find in textbooks. The state of, well, I guess at third order, these calculations, these standard traditional methods, spent about 5 years doing them, and they were done finally using effective field theory methods in 2011 by these two guys, Sturani and Falfa. This order, there's a ton of diagrams. I forgot to count exactly how many, but you get an idea of how nasty these things start to look. You know, the 5 graviton term comes in, et cetera, et cetera. But the good news is, once you know the tricks at this order, it is pretty straightforward to do things at higher order. You just tell your computer to do it. At least to write the diagrams and do all the tensor manipulations, contract all the vertices, et cetera, et cetera. And then you write it in terms of a bunch of standard integrals. At this order, the integrals are not quite so simple, but they're still standard loop integrals that you can look up in some book written by either a Russian or a German, or a linear combination of the above. So that's how it works with potentials, and really where most of the new results are is including spin corrections. So of course I did not talk about putting in spin at the vertices, but a lot of that work has been done by Porto plus Rossi from 2005 until last year. It worked out several versions. As far as computing these potentials, the effective field theory methods are competitive. That more or less gives you an idea of how you do the two-body physics, how you compute potentials, and the next step is radiation. Then I think I'll discuss that, and then I'll leave it, and then I think I'll end there. So to do radiation, we need to look at diagrams where we have one external graviton. In other words, you have to compute this quantity T mu nu that we discussed earlier. So T mu nu is given by diagrams where you have one external graviton. Like that. So to leading order, this is what it is. So there's some term like that, and next order, there's terms that look like that. There's also terms that come from radiation being emitted from potentials. This is nonlinear gravity in action. So there's a term like that, and there's terms like that as well, et cetera, et cetera. The formalism that I'm going to talk about for doing radiation appeared in a paper from 2010 that I wrote with Andy Ross. So the idea is you calculate these diagrams, you do the multiple expansion, and the answer is that the linear terms in the expansion, at least if you use a smart enough choice of gauge where the background field is covariant. The terms in the expansion look like this. There is some coefficient that has tensor indices, ij, of x0, and it couples to the curvature of this background field. I'm writing this answer in a specific frame, but everything can be done covariantly. And then let's call this thing sub E. And then there's other terms like a coupling to different components of the Riemann tensor. 0, Jik, and finally something like that, which couples to the derivative of the Riemann tensor. And the expansion goes on forever, but let me just look at the first few terms for illustration. So this is what comes out of calculating these diagrams. You just compute the linear part in the curvature that comes from these diagrams, and you read off the coefficients from the diagrams. So these are diagrams that you get by integrating out the potential mode and keeping the radiation. So this is an effective theory just for radiation alone. And so it has the standard form of an effective field theory. It couples the field in all possible ways, consistent with symmetries, and you have a bunch of Wilson coefficients that come from integrating out the short distance stuff. The Wilson coefficients are just these things. What these things are just the moments. This is the electric quadrupole moment of the system, electric parity quadrupole moment of the system. This is the magnetic parity, also quadrupole moment, L equals 2, it turns out. This is the octupole moment, electric octupole moment. And more gradients acting on the Riemann tensor will give you more and more multiple couplings. It's just a multiple expansion. The only thing is that in gravity, the multiple expansion, the moments of the distribution are moments of the energy and momentum, right? And therefore, it's not just the momentum of the particles, but the momentum of the field itself. So for example, if you calculate the quadrupole moment, well, to leading order, sure, it's equal to just the usual moment of inertia. That's the good old inertia tensor. But there's also relativistic corrections to this thing that come from those diagrams. E squared, potential stuff. So it's not just weighted over the particles, it's weighted over, if you like, the fact that these particles, their mass gets contributions from both the inertial mass and gravitational energy corrections, if you like. And if you do the other terms from these diagrams, you get stuff like 11 over 42 and x squared and x double dot, etc., etc. So that is what comes from matching onto a theory of radiation. You just get a bunch of multiple moments coupled to the radiation field. The radiation field still, its kinetic term and its interactions follow from the gravitational action. So this is not the full story. Once you integrate out the potential, you get an action like this. But then there are radiated corrections in that theory of radiation as well. So let me just tell you a little bit about those. So what we learned is that basically the radiation field can be viewed as an effective action with couplings of this sort. And now we can just use it to calculate. So for example, you can calculate L equals to gravitational radiation from the system. So now let me draw the point localized two-body system as some sort of double line, world line, and then it has a moment on it, Iij, which radiates. So that's L equals to radiation. So that's the leading order amplitude for radiating gravitons. But of course, there's also nonlinear corrections from gravity. So gravity has a 3-point coupling, so on its way out to the detector, this graviton could have interactions like that, and interactions like that, etc., etc. Calculating those, it's a double expansion. It's an expansion in 2 parameters. One of them is just the usual multiple expansion. The multiple expansion being an expansion in the size of the system, which is R, divided by the size of the system divided by the wavelength of the radiation, so that parameter is V. But there's a second expansion parameter here having to do with the fact that gravity is nonlinear. And that involves these vertices here. So here Iij is the vertex, but here's the total mass, for example. Right? The total mass of the system has a coupling of radiation, etc., etc. So the fact that these diagrams are there means that there's a second expansion parameter. And that expansion parameter is, we call it eta, is basically the gravitational size of the whole system divided by R, by the wavelength of the radiation, and that in the non-relativistic limit scales like V cubed. So in this paper with Ross, we showed how to actually handle these sort of nonlinear corrections. In particular, there are both infrared and IR divergences in these diagrams. Just to give you a quick idea of where this comes from, the leading order infrared divergence is in this diagram here, where you have the quadrupole radiating, and on its way out, the graviton that's being radiated can scatter off of the static gravitational field of this object, right? It's a point, seen from far away, it's a point mass. So it can have, it can scatter off of the 1 over R potential of the source. And if you look at the Feynman diagrams that contribute to this, let's say the external momentum is Q, well, there's going to be some sort of, let me call it K, sorry. So let me call this K. Well, the momentum flowing out of this vertex here is non-zero. It's a spatial momentum, 0 Q. This is a static source. So this is a Feynman integral that scales like d3 cubed over 2 pi cubed, because we're summing over all the momenta coming out of the source. Then it has a massless propagator for this potential here, 1 over q squared. And then it has the usual graviton propagator for this thing, 1 over k plus q squared. So that's roughly speaking, without telling you about all the tensor stuff and all the derivatives, that's how that diagram scales. So let's look at the soft limit where this external graviton has very small momentum. Actually, sorry, it has whatever momentum it wants. Let's look at the soft limit of the diagram itself. So the region of the diagram of the momentum integral where q is going to 0. Let's call this integral I. It's some sort of Feynman integral. And that limit, the integral goes like d3 cubed 1 over q squared, and then when you expand this out, it goes like, sorry, this should be k plus q squared minus k0 squared. This graviton has energy k0 and momentum k plus q. Anyway, when you take the soft limit of that, it goes like k dot q. So this is an integral that in 3 spatial dimensions goes like d3 cubed over q cubed as q goes to 0. So it's infrared logarithmically divergent. So if you were to use dimensional regularization to do this, it will go like a 1 over epsilon IR. Okay? Does that make sense? So that is an infrared divergence that shows up in the theory, but it turns out you find that, as we were able to see, that, well, one thing is you can actually understand this infrared divergence to all orders. You look at all the diagrams that have similar infrared divergences. This is the one we just saw. This one goes like 1 over epsilon IR squared. It's basically the worst divergence comes from a limit where this goes like the square of this, one can show. And finally, well, it goes like that. The pattern is there with all orders. Et cetera, et cetera. So it goes like 1 over epsilon I cubed plus dot dot dot. What we were able to find is that all those terms exponentiate. So the infrared divergences themselves exponentiate into a phase, and being somewhat schematic here, times the leading order amplitude. And when you compute physical quantities, like an amplitude squared, then all the infrared divergences cancel. So the effective theory is as it should, free of infrared divergences. One can show that more carefully than I have here, but that's basically what it is. That's basically how it works. What is the physical meaning of this infrared divergence? Well, it's just the infrared divergence. It's just the fact that Coulomb scattering is long range, or in this case, Newton scattering. It's a graviton that's scattering of a 1 over r potential. So if you like, its wave function gets distorted. It's not a plane wave at infinity. Rather, it's some sort of Coulomb wave function, some sort of hypergeometric. And the divergence is just the usual infrared singularities associated with Coulomb scattering, or Newton scattering in this problem. And the fact that the amplitude factorizes into an observable phase times the remaining of the amplitude, that actually, you can read more about that in a paper by Weinberg from 1965, where he talks about infrared photons plus gravitons, and he observes precisely the same thing for amplitudes involving quantum particles, of course, but it's the same physics, really. So that's infrared, and I guess the last thing I'll talk about is ultraviolet divergences. So if the infrared divergences appear from the fact that there's a singularity due to scattering of a 1 over r potential, the UV divergences show up from scattering of the subleading potentials. They go like 1 over r squared, for example. They are short range, so they're singular in the UV rather than the infrared. And so just to see an example of a diagram that has such divergences, where is it? Well, the first diagrams that have UV logarithmic singularities. There's UV singularities all over the place, but in dimensional regularization, most of those are 0 because they're power divergences. The first time an actual log divergence appears is in the following set of diagrams. So again, it's the multiple moment, and then we have 2 insertions of the mass, and there's 3 diagrams of this order. Those are 3 diagrams in this order. These diagrams all scale like velocity to the 6. So they're actually relevant for gravitational wave detection. If you look at, for example, I drew one diagram twice. I wasn't paying attention, sorry. that's what that is. So the fact that there's UV divergence, as you can see, because if you look at this diagram here, there's a sub-diagram which is basically the 1/r² potential of the source, right? A single object sitting by itself with some mass generates a Schwarzschild metric, and that has all powers of 1/r, right? So this is like the 1/r² term in that metric. And so in momentum space, this is a diagram that scales like 1/q. The Fourier transform of 1/r² is 1/q. And then other than that, it's the same sort of integral that we had before. This graviton has momentum k plus q, q, and k. And so this is an integral that goes like d3q. Instead of 1/q², it goes like 1/q. That's what that part of the diagram goes like. And then k plus q². So in the UV limit, where q is going to infinity, this is an integral that scales like d3q over q cubed. And so it's 1/epsilon UV. All right, so in this case, the nature, the way, the physical interpretation of the divergence is different. Well, first of all, it's a UV divergence. Second of all, if it's a UV divergence, there has to be a counter term for it. And it turns out that the counter term for it is the quadrupole moment itself. In other words, what happens is that the quadrupole moment gets renormalized. Let's say in momentum space, omega. So this is the Fourier transform of that time-dependent quantity. So there's a counter term for it, and it means that because there's a logarithmic divergence, it means that this quantity actually has to be scale dependent. It runs with scale. So there's some RG scale. And from the diagrams, you can work out what the beta function is, what the RG equation for the diagram is. If I can find it. Yep, here it is. You find that the quadrupole moment obeys an RG equation like this. It's purely classical effect. So mu d by d mu of the quadrupole moment in Fourier space goes like omega squared times the quadrupole moment. You can solve that RG equation trivially because nothing else runs in that equation, at least this order. So the answer is that the quadrupole moment is scale dependent, and if you view it at some scale, it differs from its definition at another scale by a factor of this. So to minimize potentially, so the theory is defined at a scale, the moments themselves are defined at a short distance scale, mu naught of order the orbital radius. That's where this two-body theory is defined. The infrared scale, the scale at which you're doing measurements, is order 1 over the wavelength. So what this does for you is that it allows you to understand the whole pattern of at least leading logs of velocity appearing in L equals to gravitational radiation. So this is not the whole thing, just the logs, but the leading order, the logs will look something like. And then keep going. So the next log, 91592 divided by 11025 times g squared. Log squared, same thing, plus dot dot dot, and of course you learn what all these leading logs are. By leading I mean that they go like powers of gn omega squared times a log, anything raised to that power. So we were able to predict the whole pattern of logs in that way, and then I guess a few years later our prediction was confirmed. We find the reference in a paper that actually solved the Einstein equations in a different limit, not by taking the small velocity limit, but by taking the limit where one object has a much smaller mass relative to the other one. So it's a small perturbation around the black hole, and you can solve the equations in an analytic, I mean, it's an exact in velocity, but it's an approximation in the small mass limit. And so when you take then the non-relativistic limit of that, you can check whether the logs agree, and indeed they agree. So the numbers start looking like, so if you expand our formula out to the highest order that this guy computed, by this guy I mean Fujita. I mean Fujita back in 2013 actually almost. So his last term, it looks something like this, this whole thing. But the last term he computed was something like minus 17.224239467300147 log of v cubed, velocity to be 18. He was only able to do it numerically. He actually got this digit wrong because the actual answer for the coefficient is 0.888064 divided by 3472875. That's like this number to the whatever power. And if you actually check, I think this one was off the last digit or something. So anyway, but my point is that yes, there are ultraviolet logarithms here, and they carry non-trivial information, physical information about the system, and their origin is understood by the usual methods of quantum field theory. In fact, this whole problem is understood, this whole binary problem is understood by the usual methods of quantum field theory. And that was sort of a short introduction to the ideas. So I think I will end there. That's it.